Hello everyone. This is the tutorial for the electric field mapping laboratory. You have it in front of you on my screen. The idea with this lab is to explore electric field lines and equipotential lines. It's very simple. Even in a lab, in person, it's a more qualitative lab. The only thing that you have to worry about is to understand the physics behind the drawing and illustration of electric field lines based on equipotential lines. If you're using exploration physics, the instructions are pretty clear. You are going to use the software and you're going to build a charge and another charge. And as you can see, these are the electric field lines. What you should do is you should draw the equipotential lines. And I'm going to show that on the board in a little bit. For the software, if you don't have exploration physics, or if you don't want to use it, you click here and you want to open this. Well, let's actually do it from the very beginning. You click here, you can close this, and you have that. So basically what you can see theoretically in a textbook. What you can do here, though, is you can show grid, you can show the equipotential lines. For example, here, or here, here, here. And as you expect, they are circular. And the reason is because the electric field lines are also curved in a sort of elliptical shape between positive and negative. And we know from the theory that the equipotential lines and the tangent vector to the electric field line make an angle of 90 degrees. So what you should do, following the instructions for a two-point charge arrangement, is basically labeling those electric field lines and then drawing or labeling the equipotential lines, and then describe what you observe. It's actually pretty simple. Now, let's actually take a look at a different arrangement, like the one-point charge and the parallel plate. If you're using the exploration physics, you can create a parallel plate like you see on my screen. You cannot do that, unfortunately, in the other software, but I'm giving you recreated data there. So let's take a look at the logic behind this. All right. You see, you have the negative and you have the positive. So the electric field lines for a positive charge, they go away. And for a negative, they come towards the charge. And that's important when you're solving problems of electric field lines. And it's going to be important when you do the individual questions. So for the two-point charge, positive, and then here negative, right? The amount of lines leaving the positive, if it's 1, at least 1, and then 2, and then I can do another one, 3, 4, and then 5, 6, then also 5 and 6. So because they both have the same magnitude of charge,
Attention is
Q and negative Q,
of a Burgundy Chevy
So,
Trax, license plate
the amount of
N8
lines leaving this
DM.
has to be the same as the amount of lines entering here. If you
Again, a
had
Burgundy
double,
Chevy Trax.
if you had
Please come move your vehicle by the Roosevelt Gate.
2Q and negative Q, right? If you have say again, 6. And like this. Again. You had 6 again, leaving. Entering here will be, okay, there's 4 here. So I need 1, 3, 6. I need actually 8 leaving. 8 is twice 4. So there are twice the amount of lines leaving to Q than entering negative Q. That's the logic behind electric field lines. And then the equipotential lines. You can draw one on the middle, and then the tangent vector, which is this, makes a 90-degree angle with the equipotential line. That's why we draw them like this. All right? That's the logic behind that. Now, what about the point charge and the parallel plane? How do you draw? Because in the file, you are given the equipotential lines. So you are doing the opposite now. With equipotential lines, you are drawing the electric field lines. And think about it. For 2 parallel plates, and you have that in the arrangement in the last one. For 2 parallel plates, if you have positive, 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 negative, 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 the electric field lines go from the positive to negative. Like this. Right? So the equipotential lines are just vertical lines. All right? So for a point charge on a parallel plane, you're going to combine. All right, that's the idea. And you can see that from the equipotential lines. Okay, I'm not going to draw it because that's part of what you have to do, but that's basically the idea behind it. Now, for the 2 parallel plates, you are going to draw the equipotential lines. That's basically this, but then you have to do a calculation. You have to calculate the electric field given the potential, right? So let's go to the file. All right. In here for the last arrangement, you're given this. So those are the equipotential lines. You can draw the electric field lines easy, right? And there are a couple of things that you have to notice. The potential is decreasing. And the voltage was 8. So you can easily figure out where is 8 and where is 0 volts. Now, you're going to complete this table. You're going to find the electric field using the equation that you should have covered by now in the lecture, where electric field is negative change on potential over displacement, or delta X. So let's do it for these 2 points, 6.68 and 5.36. Yeah, so basically here, we're going to find the electric field at 2.6, right? Yeah, so we're going to use these values, all right? I'm going to draw them on the board. And let's find the value for the electric field. Now you're finding the magnitude. So my magnitude of electric field is negative delta V over delta X. What's that? What's this? Sorry, something there. So you're going from right to left. So 5.36 minus 6.68 over the distance 3.5 minus 1.8. Negative. So I'm going to show you now what I have on the whiteboard. That's how you do it. So then I'm just gonna use the calculator, right? So basically, you are, oh great. Sure, charge that during the summer. So 5.36 minus 6.68 is negative, that's okay. So negative 1.32, negative 1.32 over 3.5 minus 1.8 is 1.7. So then you're gonna get 0.776 or yeah, 0.776 volts per meter. Oh, wait a second now. 3, 2, I need 2 here. 0.78 volts per meter. So there you are. All right, so that's how you complete the table, and then you have to write your discussions. Very simple. All right, let's actually take a look at those individual questions. All right, so the lab should not be a problem. You submit this, then you go back here. I'm gonna give you hints. I cannot solve these questions for you guys, but you know you can always send me an email if you have any trouble. Oh, that's a submission. Individual questions here. So let's see what I have here. Okay, so you're gonna find the electric field of this dipole. This one, I already explained how to do that. 4Q, negative 3Q. So find a number that is proportional to 4 and 3, 24. So if you have, say, 24 lines leaving 4, right? How many lines should leave 3? Maybe 24 is too much. Make it 12. All right? So it's just that. This one, I'm gonna give you a couple of hints for that, right? So for number 1, they give you a positive and a negative. So that's a question that you're probably gonna do in a lecture. If you have the X and Y axis, and they want you to find the electric field at position P at distance R, where this is Q and negative Q. This is D over 2, and this is point R here, or distance R. Look, it's kind of what you did in physics 1. Positive Q, guys. Remember what I said? You're gonna draw this, and the vector electric field at P is like this. That's it to that. For negative Q, you're gonna draw this line, but be careful though. Spin here. That's, let's call it E2, E1. See what I'm saying there? And what you're gonna notice is that the overall direction is gonna be on the y-axis because these both have the same charge. Now, this is 90 degrees. So what's the distance here? That's the square root of R squared plus D squared over 4, which basically is 1 over 2 square root of 4R squared plus D squared, right? And it's the same as this. So this is also 1/2 4R squared plus D squared. So then how do I find E1? I want to show you E1. E1, if I want to find the magnitude, I use the equation KQ over R squared. right? That's the equation. What's R is this, that. So for Q, and remember, the magnitude of the charge, right? If you're looking at the magnitude of E1, you're taking as the magnitude of Q. The directions are given in the drawing. K, Q, what's the distance squared? 1/4, so I'm squaring it, and the square of the square root, 4r squared plus d squared, which basically is 4kq over 4r squared plus d squared. So that's basically E1. So that's this, the magnitude of that. What you need to do then is to find the overall, you're gonna break it into components, right? You have this angle, let's call it angle theta, right? Because of the symmetry, this is an isosceles triangle, right? This angle is also theta. All right, so these two angles are the same. That's why when you do this, the x direction will cancel. You have to show me that though. Why does the x direction cancel? And then on the y, you're gonna have this going down, this going down. You break into components. Now, that angle theta, what's the sine of theta? You need sine and cosine, but mainly sine. Sine of theta is opposite over hypotenuse. So don't be surprised that a lot of the terms that you're gonna use are gonna cancel. Like that. So my sine is this. Okay, that's the sine of theta. You need that for the y component. Sorry, for the x component. You need that for the x component. Yeah. Wait, cosine. No, sorry, you need that for the y component. My bad. So that will be for the y component. For the x component, you will need a cosine. But as I said, it's just proving that they cancel. And it's obviously right why they cancel. Yeah, and then basically you will have them on y, you add them, and you have an expression. All right, so that's basically the idea with question 1. Now, what about question 3? That gives you numbers. So compute the value of the electric field inside the, right, guys? They give you the x direction and the y direction, right? And they give you the speed. So using kinematics, you can find the time it took for the charge, for the electron, to reach the end of the plate, right? That's a free fall projectile motion. Now there is no gravity. Why is the electron being deflected like that? Because of the electric field. The electric field provides an acceleration because if there is a charge inside an electric field, you have an electric force. If there is a force, then you have an acceleration. Okay? Now, subatomic particles like electrons, protons are too small, are very low massive, basically negligible mass. So gravity doesn't really play a big role in subatomic particles. So then we only care about the acceleration due to the electric field. And that's how you compute the electric field. So basically, guys, what you're gonna do in there is you're gonna first find the time. All right? So you are given on X. X equals to 2.00 centimeters, which is basically 0.02 centimeters. So x is equal to Vx delta t. I want to show you guys the equation. The speed is 7 times 10 to the 6. Okay. That now Vx is 7 point, right? So what you're gonna do is x equals to V and you can find delta t. Now, why do you need this step? Because on y, you're also given the vertical distance. You're given in the vertical distance in that problem is 0.150. So on y, you can say y, or yeah, y. Y final minus y initial is 0.150. Meters or centimeters? Let me see. Pretty sure it's centimeters. Yeah. If the electron is doing this, the initial vertical velocity is 0. So your y is 1/2, not g, a, t squared, and that's t. So this t will go here. You have y, you can find the acceleration. Why do you care about the acceleration? Because mass times acceleration is equal to electric force. And what's electric force if you have the electron charge? Well, guys, the electric force for a point charge is equal to the electric field times the charge. You need this equation. Now that's force. That's also equals to mass times acceleration. The mass of the electron, if it's not there, you can look in a textbook, but mass of the electron 9.11 times 10 to the negative 31 kilograms. Be careful with your calculations, all right? Just as a hint, electric fields are normally quite large. So your answer for this problem should be large. All right, you should not be getting tiny electric fields. But that's basically the procedure. So you're combining some kinematics and Newton's laws. All right, it's a very good problem, and I'm sure you're gonna do problems like that in the lecture. All right, so that's basically it. Remember, guys, you can always send me an email, and we can set office hours if you have any further questions. See you all later. Have a nice rest of your day.